So let's look at the case of non-symmetric vibrations of the drum. And so in this case, the dependent variable, the displacement of the drum head, depends on radius, angular position, and time. And so the idea of separation of variables is applied again. We separate the dependencies on the independent variables. We say that the radial dependence is given by a function capital R. Azimuthal dependence or angular dependence is given by a capital theta function, and time dependence on time is through a function capital T. And we substitute this in the partial differential equation and separate the dependencies as we mentioned before. And so that leads to this system of equations that associated with the theta variation, which is a direction in which the variation must be such that they are cyclic over the complete period of 2 pi. Theta goes from 0 to 2 pi, and when we are back at 2 pi, we are back at where we started. And so for the solution to be smooth, we must have a 2 pi periodicity of the solution in theta. And so the theta variations therefore must satisfy this condition where m is an integer, and the rest separate out in this way. And so when we look at in particular the radial structure here, the radial variation is governed by this equation, which is the Bessel's equation, Bessel's ODE, but it's the Bessel's ODE for mth order Bessel function. And so its two linearly independent solutions are j sub m and y sub m, and again y sub m blows up, and so we keep only j sub m. And so the solution overall, once we work out the details, can be expressed in this form, where the radial shape of the eigenfunction associated with radial variation is given by this dependence. With respect to theta, it varies in a sinusoidal way with sine m theta and cosine m theta with unknown constants that have to be determined by initial conditions. And time variation is also sinusoidal, and cosine with natural frequency, which depends on the mth zero of the nth order Bessel function. And so actually I have a little typo here, so let me fix this. Like we have here, nth zero of the mth order Bessel function, this should be switched here. M and n should have their appropriate place, and so it should be n here, and m over here is the mth order Bessel function, and it's the nth zero of it. All right. So this is now the correct representation, and what we're going to look at is we're going to plot this up again and get some sense. So this is a very nice example because with simple analysis we get solutions in closed form, and we can plot them up and we can get a physical feel. But even more importantly, if you're into music or you're into vibrations, you're into setting up little experiments, demonstrations, this is something you can easily do and visualize with a high-speed photography. You can take pictures, or you can sprinkle some powder on top of a drum and so on, and then because of the drum vibrations, the distribution of the powder changes and it settles down in places where the drum is not moving much. These are node lines or nodal lines, and thereby you can visualize the pattern if you can't do high-speed photography to see the displacement and so on. So these are nice, cool things. Of course, other places of waves and vibrations, vibrations of a liquid in a circular tank. You can tap on the tank on the side, or drop a stone in the middle and see shapes of waves that are produced in a circular drum or a circular container. And again, if you do analysis, you will find that Bessel functions show up, and Bessel functions show up in many other places and so on, and likewise other special functions associated with problems in mechanics, problems in physics, problems in other fields show up naturally, and they are very familiar, and you should get to know them so that you can use them when they arise.